Hello and welcome back. Lecture 2-3, Decibels. The objectives of today's lecture is to define decibels for measuring power gain or loss, and to find physical and signal power as a power ratio or level measurements in decibels. Given two physical powers, P1 and P2 in watts, the ratio P1 over P2 is commonly expressed in decibels as 10 log base 10 of P1 over P2. Please do not confuse this with voltage ratios, which most students have studied in their circuits course, which is 20 log 10 of V1 over V2, and it's also expressed as decibels. In this lecture, we will explain why and what the difference is when you use 10 log base 10 or 20 log base 10. The logarithm is always taken as base 10. Be careful because in MATLAB and Maple, the command for base 10 is log 10, where log is actually the natural log, ln. Background. The decibel was standardized by the telephone system in the 1920s in order to measure line loss. Suppose you have a standard length 1 mile of telephone cable. The gain is P out over Pn. When the gain is less than 1, it is customary to use loss instead of gain, where loss is the reciprocal of gain and is Pn over P out. Now consider if you have 2 miles of cable. Then the loss would be Pn1 over P out 2, or the product Pn1 over P out 1 times Pn2 over P out 2, or the product loss 1 times loss 2. This could be a very large or very small number, and by expressing it in decibels instead of multiplying, when the systems are cascaded together, it makes a quick calculation of addition. So the loss in decibels would then be 10 log base 10 of loss 1 plus 10 log base 10 of loss 2, because the log of a product is the sum of the logs. So that would be the loss in 1 in decibels plus the loss in 2 in decibels. There are two other reasons for using a logarithmic scale. Number one, a much greater range of values can be plotted on a given graph, or fractional values are magnified and large-scale values can be more compact. So in other words, the numbers 1 to infinity would be compressed because you're plotting multiples or powers of 10, and smaller values 0 to -1 would be expanded for the same reason. Human senses such as hearing tend to respond logarithmically, such as octaves in tone when frequency changes and doubles, or it is exponential for equal steps, such as the knob on a stereo from 1 to 10 is a log of 10, and it multiplies in power and intensity of light and frequency of sound are generally a log scale, or thinking about octaves on a piano. The basic unit bell is log base 10 of P1 over P2, named after Alexander Graham Bell, but is seldom used. The preferred use is the decibel, which is 1/10 of a bell. Decibel is not a dimension because P1 over P2 is dimensionless, so decibels is always a ratio. So a loss in decibels would be 10 log base 10 of loss, or 10 log base 10 of Pn or P out, or negative 10 log base 10 of P out over Pn, which is the gain, or negative 10 log base 10 of gain, or the negative gain in decibels, i.e. a loss of 3 decibels is the same as a gain of -3 decibels. Example 1. The loss ratio for 1 mile of phone cable is 2. What is the loss for 1.5 miles of phone cable? So here's an example where we can see the benefits of doing these calculations with decibels, because it's very hard to quantify what a loss of 1.5 miles would be in absolute terms. But a loss for 1 mile of cable in decibels would be written as 10 log base 10 of 2, or 3 decibels. So the loss in decibels for 1.5 miles of cable would just simply be 1.5 times 3 decibels, or 4.5 decibels. So that's a lot easier to compute than trying to compute this value in absolute terms, which would end up being 2 raised to the 1.5. This is something you would have to do in your calculators. However, back in the 1920s, they would have had to do this with a slide rule, which was rather difficult. Power level measurements. Decibels are also used for physical power level measurements. To get an absolute value in decibels, it has to be relative to a reference value so that we have a ratio. The common references used are 1 watt and 1 milliwatt. So the power in decibels would be 10 log base 10 of the power over the power reference. So if the reference is 1 watt, then we have 10 log base 10 of P over 1 watt, and the units are dBW. Or if we have a reference of 1 milliwatt, then we have 10 log base 10 of P over 1 milliwatt, which is units of dBm. Example 2. What is the power for a 30 watt source in dBW and dBm? So first, the power in decibels would be 10 log base 10 of 30 watts with respect to 1 watt. So that equals 14.8 dBW. Or the power in decibels would be 10 log base 10 of 30 watts divided by 1 milliwatt, which is equal to 44.8 dBm. And so what you should notice here is there is a 30 dB difference, which makes sense because that's the same as an absolute multiplication by 1,000. Example 3. Suppose a 2 watt source drives an amplifier with a gain of 2. What is the power level and the gain? So we will do this with respect to 1 milliwatt and 1 watt, so we can see the difference. So P out is equal to P in times the gain, or in terms of decibels, we're going to have 10 log base 10 of P out with respect to 1 milliwatt is equal to 10 log base 10 of P in with respect to 1 milliwatt plus 10 log base 10 of the gain. So this means that P out in decibels is equal to 10 log base 10 of 20 watts over 1 milliwatt plus 10 log base 10 of 10. So that equals 33 dBm plus 10 dB. So this first value is the power level, and the second value is the gain. Now it may look like we're mixing units, but we're actually not. Remember, this one is in dB because this is a ratio, and this one is in dBm because it's a power level. So what happens is when you add them together, the final answer is 43, and the units are dBm. So when you have a level, it's dBm or dBW, or when you have a ratio, it's just dB, but when you add them together, that is also a level, so it's dBm. So now let's see what the answers would be with respect to 1 watt. P out in decibels would then be equal to 10 log base 10 of 2 watts with respect to 1 watt plus 10 dB. So this is 3 dBW, the power level, plus 10 dB, the power ratio, and the final answer would be 13 dBW. Example 4. A system has a signal power of 25 dBm and a noise power of 15 dBm. What is the signal to noise ratio in decibels? So to calculate the signal to noise ratio, we'll have that SNR equals the ratio of the power in the signal to the power in the noise. Or we can write this as the power in the signal with respect to 1 milliwatt times 1 milliwatt over the power in the noise. So that means we're doing both with respect to 1 milliwatt. So this becomes 10 log base 10 of the P sig over P noise which equals 10 log base 10 of P sig with respect to 1 milliwatt minus 10 log base 10 of P noise with respect to 1 milliwatt, which equals a signal to noise ratio in decibels of 25 dBm minus 15 dBm. And notice those are dBm because those are levels, but when I subtract, it's going to be a ratio. So this is actually 10 dB. This is a power ratio. No M because it is not a level. So here we have a plot of the signal to noise ratio for several different values. Notice that when the signal to noise ratio is 40 decibels, we have a very clean cosine wave. And then as the signal to noise ratio is decreased, what you start to see is that the signal is becoming corrupted with the noise. By the time the signal to noise ratio is at negative 10 decibels, we now have mostly noise and the signal is lost. You're actually going to see this in one of your labs. Decibels are also used for signal power. Consider an operational amplifier where the input signal is in volts RMS squared and the output signal power is in volts RMS squared. The gain is given by 10 log base 10 V out RMS squared divided by VI RMS squared. So notice here, this is where the 20 log base 10 comes from, because if we changed it to a ratio of voltages instead of power, we have 20 log base 10 of V out in RMS over V in RMS, because when you square in logs, it becomes a multiplication by 2. Note that the signal power ratio means that R canceled out if it is the same R. Note that you're going to have to judge for yourself from the context whether a ratio in decibels refers to a physical power ratio or a signal power ratio. Level measurements. For level measurements, we need a voltage reference, just like we did for a power level measurement. So the voltage in decibels would be 20 log base 10 of the voltim RMS divided by the voltim RMS reference. So common references are 1 volt and 1 millivolt, kind of like how we had 1 watt and 1 milliwatt. So the voltage in decibels would be 20 log base 10 volts RMS with respect to 1 volt, or 10 log base 10 volts RMS squared divided by 1 volt squared in dBV. We can also have voltage in decibels as 20 log base 10 VRMS with respect to 1 millivolt, or 10 log base 10 VRMS squared with respect to 0.001 volts squared, which would have units of dBmV. Note that we don't put millivolts squared in the denominator of that second equation because it's ambiguous, so you should always write 0.001 volts squared. Example 5. For the following operational amplifier, the input voltage is A cosine omega t. Find V naught of t, then find the gain in decibels, dBV, and dBmV. Assume A is equal to 0.1, and then find the output voltage. So the first thing you should note here is that we have an inverting amplifier. An inverting amplifier has a gain equal to negative RF over RI, where the feedback resistor RF is 100 kiloohms and the input resistor RI is 1 kiloohm. So the gain is negative 100. So this means that V naught of t is equal to negative 100 times Vi of t. We can also write V naught of t as negative 100 times A times cosine of omega t. So we can write the input in RMS values, VI RMS, as A over the square root of 2, and the output in RMS values as 100A over the square root of 2. And the gain in decibels we can write as 20 log base 10 of the ratio of the voltage output to the voltage input. So that's 100A over the square root of 2 divided by A over the square root of 2, which equals 40 decibels. And note that the units are decibels because that's a ratio of two voltages. V out in decibels can be written as 20 log base 10 of 10 over the square root of 2 with respect to 1, and that's 17 dBV because now that's a level where it's a ratio of the output with respect to 1 volt. We can also write V out in decibels as 20 log 10 of 10 over the square root of 2 with respect to 1 millivolt. So that's volts with respect to millivolts, and that ends up being 77 dBmV. And once again, that's a level. And this concludes example 5. Example 6. If V of t is 5 cosine 2 pi 1000 t plus 30 degrees, what is the voltage in dBV and dBmV? So first we find the RMS voltage. The RMS voltage is 5 divided by the square root of 2. So the voltage in dBV would be equal to 20 log base 10 of 5 over the square root of 2 divided by 1, which equals 11 dBV. And the voltage in dBmV would be 20 log base 10, 5 over the square root of 2, and that's in volts, divided by 0.001, that would be millivolts, and that equals 71 dBmV. And once again, we see that these are both levels. Example 6. For the following passive filter, what is the loss in decibels? Once again, this is an RC circuit with a voltage measured across the capacitor. So as we've seen before, this is going to be a low-pass filter. The way that I can quickly tell that is because a capacitor, as the frequency goes towards infinity, becomes a short circuit. So that means the voltage is dying off. So this is a low-pass filter, which means it has the following shape, where once again, the cutoff frequency would be 1 over RC. So the transfer function or frequency response, h of j omega, is 1 over j omega c divided by r plus 1 over j omega c. And that can also be written as 1 over 1 plus j omega rc. And that's the ratio of V out over Vn. So the magnitude of h of j omega squared, which would be the ratio of powers, is 1 over 1 plus omega squared r squared c squared. The way to quickly see this is to multiply 1 over 1 plus j omega rc times 1 over 1 minus j omega rc. Because when you take the frequency response times its conjugate, that gives you the magnitude squared. So the gain in decibels would be equal to negative 10 log base 10 of 1 plus omega squared r squared c squared. And the loss in decibels would be equal to 10 log base 10 of 1 plus omega squared r squared c squared. Remember, there's a negative relationship between the gain and the loss. Finally, to summarize all of our new units. So we have physical power and signal power. Although I will tell you, typically in this class, we're referring to signal power. You did physical power in your circuits course. So for physical and signal power, if it's a power ratio, they're both in decibels, which can be a bit ambiguous. So you have to look at the context of the question to determine whether you're talking about physical power or signal power ratio. However, level measurements are rather clear because for physical power, they would be dBW and dBm. However, for signal power, we would have dBV and dBmV because signal power absolute is expressed in terms of volts. Volts squared, not watts or milliwatts. And this concludes lecture 2-3 on decibels.